Good evening, everyone. My name is Abhishek Patel. I am from Department of Civil Engineering, Indian Institute of Technology, Madras, and I am working under Professor Benny Raphael as a PhD research scholar. The topic of my presentation today is reducing carbon emissions in 3D printed RCC slabs. The outline of my presentation: first we will be introducing about the study, then the major objectives of the study, then the methodology we adopted, results, conclusion, and finally the recommendations for the future research. The concrete 3D printing is an additive manufacturing technique that enables construction without formwork using input from a CAD file. There are various advantages of concrete 3D printing. No formwork is required, a high productivity, sustainability potential, a cost saving potential, etc. But apart from these advantages, there are various challenges in full scale implementation of 3D concrete printing. First one being lack of 3D printing of bending and tension bearing members, then the lack of full scale automation and high cement content in 3D printable mix. To reduce the consumption of material and subsequent carbon emissions, there is a technique that is used in construction industry called conventional filler slabs, in which filler materials like clay pots, clay tiles are used in zones where concrete is not functionally required, and then the concrete is poured so that the material consumption is reduced and subsequent carbon emissions as well. But there are various disadvantages of this technique. First one being high carbon footprint of filler material. So the production of the carbon clay pot itself produces high amount of carbon emissions, which neglects the carbon emissions which was reduced due to the consumption of the raw material. High supervision is required, and also the filler material coming in the contact with the rebars can cause corrosion in the longer period of time. Hence, we came up with a technique called 3D printed filler slabs, in which the advantages of 3D concrete printing and filler slabs are being combined to nullify the challenges in full scale implementation of 3D concrete printing, as well as the challenges in conventional filler slabs. We are using recycled plastic waste as filler material instead of clay pots to reduce the carbon emissions generated by the clay pot. The objectives of the study is to propose an automated method for 3D printing RCC filler slabs using recycled polyethylene waste, achieve a reduction in raw material use and carbon emission in slab manufacturing, evaluate environmental impact through a life cycle carbon emission assessment. To start with the study, we conducted an exploratory study in which a small slab panel was printed. The objective of the study was assessing feasibility of 3D printing a concrete filler slab. So to understand how we printed the slab, so on the right hand side, on the left hand side, you can see a solid RCC slab. We printed this slab with three different layers. First layer was the cover layer, which was printed to protect the reinforcement from the environmental exposure. The central layer is the tension layer, in which maximum amount of material consumption will be saved, and then the top layer is the compression layer, in which the concrete is most required to take the compressive loads. Here we can see the sectional view, cross sectional view of the filler slab. The purple balls here are the filler materials, and on the sides is the concrete. To know further how we printed the slab, we can see here the process. First we printed the cover layer, then we placed the reinforcement bar over the cover layer. The reinforcement, then to print the tension layer, we just printed over the reinforcement cage, and the voids were generated. These voids were filled by recycled plastic, which was mechanically compressed into cylindrical balls. These cylindrical balls filled the voids. Once the voids were filled, the compressive layer was printed on the sides. Once the layers were printed, they were grouted using self-compacting concrete. After the assessment of this slab panel, we found that we were able to reduce the material consumption by 20%, and there was a 15% reduction in carbon footprints through material saving. The challenges we faced were manual placement of rebar and fillers. So the placement of rebar and filler manually was a challenging task, given that just after the printing the specimen was in a fresh state, and hence it was a time consuming and inefficient process. Hence we came up with the conclusion that we need to automate the 3D printing of concrete filler slabs. To start with the automation process, we came up with a preliminary robotic system. So here you can see a 3D concrete printer, gantry 3D concrete printer, which has a printing head which will be used for printing. It is integrated with a robotic gripper which will be used for which will be used for pick and place operations, as well as here is a grouting system which will also help in grouting in the final stages of the printing. This is a overall plan view. Here we have stacked the rebar cages, and here we have stacked the filler elements. This is the printing head, so it will be used for printing, and when required, the robotic gripper will be used to pick and place the rebar cage and the fillers from the desired locations. To investigate the preliminary automation concept, we took a 6 meter by 4 meter case, or we took a case of 6 meter by 4 meter RCC slab, and we divided into 6 equal panels. These dots represent the voids generated after the printing of the tension layer. And here you can see the rebar cage. So the rebar cage is stacked over here, and the filler materials are stacked over here. Once the tension layer is printed, the filler material will be picked by the integrated robotic gripper and picked and placed one by one into each of the void. To investigate the carbon emissions of the process, this is the system boundary. The system boundary, we took a cradle-to-gate approach, in which we started with the production of the raw materials, whatever the raw materials are required, and then the transportation of the raw material into the different subsequent facilities, then the transportation of the fillers to the offsite 3D printing plant, and then the final product will be transported to the construction site. So this is the cradle-to-gate approach that we took for the carbon emission assessment. For evaluating the carbon assessment of the methodology that we are proposing, we took three different scenarios. All the three different scenarios are 3D printing scenarios. The first scenario is 3D printing of the slab without any filler, then the 3D printing with the clay pot as filler, then 3D printing with recycled plastic as filler. As here you can see, the third scenario is having the least amount of the carbon emissions, and the carbon emissions in the production of the filler is significantly reduced from the case 2, which was clay pot, and the which was mechanically compressed recycled plastic in case 3. So the numbers are here. So 20% reduced material consumption and 33.5 reduced carbon footprints were observed overall. There was a 97% reduction in emission and for the production of the filler element from case 2 to case 3. Also in case 3 you can see a green part on the bottom, which represents that we have captured the emissions that would have caused if this waste plastic would not have been repurposed and would have been incinerated. So we have took around 11% of the total plastic that we used as incinerated and calculated the carbon emissions that we have saved. The challenge we faced here was that we used a single gantry, hence no parallel activities were there, and hence a high process time was observed. Also, through this investigation we came up that there is a need for further automation and optimize the overall process with respect to time and overall carbon emissions. Now, as we will be including more automation equipments and machineries, the problem is not only limited to the carbon emissions, but it goes towards time and cost as well. So now it becomes a multi-criteria decision-making problem, which will be taken into the further studies. The conclusion of the study was automated 3D printing with recycled polyethylene fillers shows potential to cut material use and carbon emissions. Repurposing polyethylene waste avoids emissions from incineration of same if not repurposed. Lower dead load in slabs further reduce emissions in foundational construction. Automation has potential to enhance precision, reduce human error in filler and rebar placement. The recommendation for the future research is extend for this research to operational and demolition phase as well. Investigate other recycled material as fillers for further sustainability. Apply automation to other workflows of overall process. Refine life cycle assessment using real world transportation data. These are the few references. We would like to thank Serb India for funding this project. We would also like to thank TLC2 and SBI Foundation for financially supporting the project, and also Tavasta for providing the 3D printer which was used in the study.